Continuing on with two more examples of circular motion. Number 3, what if you were swinging from a chain that was 9 meters long? Okay. Well, how is this an example of circular motion? Well, because this path right here is part of a larger circle all the way around, right? So if you had enough speed, you could conceivably swing all the way around in a circle. So with that in mind, let's break this one down. Let's draw the velocity and acceleration vectors. So if the girl was traveling counterclockwise in side view, we're again looking this way. That's counterclockwise. So let's put the girl here. She's kind of at this part of the circle. And her velocity would be this way, which is tangent to the circle. It's kind of always like that. And her acceleration is towards the center. Again, if the girl were to jump off the swing at this particular moment in time, she would go straight out like this, right? That's how we're getting the velocity vector. Those are at right angles to each other, as they always have been. Let's draw a free body diagram. So here's the girl swinging, and she's experiencing a few forces. First of all, she is experiencing the force of gravity, of course. And then there's got to be something that's pulling her into this semicircular path, right? Well, that force is this way, along the chain, but it's and if you call this, by the way, if you call this tension, you're pretty darn close, right? Because there is a chain that's pulling towards the center of that circle. But she is not literally being pulled by the chain. She is literally being pulled by a support under here, right? She's sitting on a seat. The seat is here that she's sitting on, okay? So if she's actually being pulled into a circle by the swing seat, then we should call this a normal force, to be a little bit more specific. So which force is acting in the centripetal direction? Well, it's the normal force. It's the swing seat that's actually pulling her into a circle. So let's calculate her velocity if 1/6 of a circle takes 1 second. 1/6 of a circle takes 1 second. That means the entire circle would take 6 seconds, right? If just this portion takes 1 second, then the entire thing would take 6 seconds. Velocity still 2 pi r over t. We know that the radius is, it's right here, 9 meter radius. And the time it takes to go all the way around is 6 seconds. So this velocity is going to be 9.42 meters per second. And I'm kind of running out of room here. 9.42 meters per second. Continuing on, her acceleration, therefore, is velocity squared divided by the radius. So there's the 9.42 meters per second squared divided by the radius of 9 meters. Gives us an acceleration of 9.86 meters per second squared. And that's almost exactly 1 g. Finishing up with one more example. Okay, so if you've been following along, these examples have been pretty different, right? So in example 1, we've had a loop that we're looking at from the side where the normal force is a combination of two forces. Where the centripetal force is a combination of two forces, normal and gravity. In number 2, now we've got friction as a centripetal force. In number 3, now we've got a normal force from a seat that's acting centripetally. Number 4 is going to change it up even one more time because now we're going to go into satellite motion around Earth, okay? So here's the satellite, and it's going in Now, this view makes it look like it's an elliptical orbit, but that's just because it's sort of at an angle. If you could see it directly from above, here would be the satellite with its two little solar arrays out on the sides going around in a circle. Okay, so we're now going to look at it like from top view. Okay, and if this motion is clockwise, that would be this way, clockwise, then what would be the direction of the satellite's velocity at this particular moment? Well, it would be that way, right? And the acceleration would be this way. And my mistake, let me actually straighten that out a little bit more. According to this picture, the satellite is really right against the side. So the velocity should be straight down, and the acceleration would be straight that way. Okay, those are, again, at 90-degree angles. All right, if we could look at the satellite in top view, which is the view that we were looking at here, and we drew a free body diagram of it. Here's that satellite. Here's its two solar arrays. What forces would be acting on that satellite? This is a tricky one. It's beyond Earth's atmosphere. It's not in contact with anything. And yet there is still a force acting on the satellite, which is causing it to orbit the Earth. And it is the Earth's, it is the gravitational interaction with the Earth. And that specifically would be pulling this way. Right, towards the Earth. So what's the centripetal force? Gravity. Gravity is acting as the centripetal force in this case. And now what's the velocity? Well, one orbit is going to take 24 hours. And over here, we actually have some information. Its distance from the center of the Earth. We're gonna assume that this is the 36,000 kilometers from the center of the Earth. Okay. For simplicity's sake, okay? The way that the distance is being drawn is here to Earth's surface, but I'm going to simplify it and say that that's all the way to the center of the Earth, okay? So velocity is 2 pi r over t. And I'm going to use some space down here. So this radius is 36,000 kilometers. And we need that to be in meters, right? So we'll do some dimensional analysis. There's 1,000 meters in 1 kilometer. So this is going to be 3.6 times 10 to the 7 meters. And then we're told that the orbit takes 24 hours. So we're going to do some more dimensional analysis to figure out how many seconds it takes to go all the way around in one orbit. So the time is 24 hours. There are 60 minutes in 1 hour. So hours goes away. And I probably could have showed that up here too. And then we want to go from minutes to seconds. There are 60 seconds in 1 minute. So now minutes go away. Okay, so there are 86,400 seconds. So now we've got our radius in meters and our time in seconds, and this will give us a velocity in meters per second. So here we go, 2 times pi times the radius of 3.6 times 10 to the 7th meters divided by the time, 86,400 seconds, gives us a velocity of 2,617 meters per second. By the way, a rough conversion from meters per second to miles per hour is just double it. So this is going about 5,000 miles an hour. That's really fast. Okay, what's the acceleration though? V squared over r. The velocity is 2,617 meters per second. Square that, divided by the radius of 3.6 times 10 to the 7th meters. We get an extremely small acceleration, 0.19 meters per second squared. That is, of course, because the orbital distance is so big, right? It's 3.6 times 10 to the 7th meters away, and so the acceleration is very small. All right, so that's been 4 very different examples of circular motion where the centripetal force keeps changing in each scenario.